Hello, chemistry class. Before we start, I'd like to thank our resident memer. I can't find the message. I saved it to my phone, so I put it in the video, but I can't find who it was. So please take credit for it in the group chat. I don't remember who sent me this meme, but thank you. Remember that if you send me memes, I'll shuffle you guys in. I've already got like 3, but I need some for next week, so please send them in. Hello, ladies and germs. Happy Thursday. Welcome to chemistry. So we've been talking about acids and bases, looking at my calendar. So far we've covered the intro to acids and bases and the equilibrium, and we quizzed on that. Then we covered the pH scale and the pOH scale. And today we're talking about acid and base strength. I had planned for a quiz tomorrow. I'm probably going to take one more day on acid and bases and then schedule a quiz on Monday. That'll be a take-home quiz, which basically will mean that you won't have a class on YouTube, or rather, it won't mean that you won't have class. I'll post a video that has the questions of the quiz in the video, and you'll just do that at home like you would homework and text me a picture of it privately um, so I can grade it. So, let's talk about acid and base strength. So, what would it mean if I said, I have a strong acid, or I have a weak acid, or if I said, I have a strong base, or I have a weak base? How do you know? Well, note time. Strong acids have things in common. Number one, they give up protons easily. What I mean by that is think about, um, let's write some examples. Think about maybe hydrogen bonded with iodine. That's that sort of supercharged molecule that we were talking about the other day. Um, the ones that have super high pH or super low pOH. It's sort of, it's so ready to break apart that when it does, it just goes. It's a strong acid. It just wants to give up that proton easily. That H is going to rip right off that I, and it's going to create something new. Um, Maybe the one you guys are all familiar with, HCl, is another super strong one. Let's look at an uncommon one that you don't see very often. We got HNO. My eyes are bad. 3. And one more just for fun, H2SO4. Which in college they gave me H2SO4 in like every single problem. It was ridiculous. We always did H2SO4. I knew the chemical mass and stuff by heart. We used it so much it was ridiculous. So, they give up protons easily, they are product favored, and they ionize completely. Now, what does product favored mean? Product favored means you're going to end up with a higher concentration of products than you will reactants. So in other words, I mix some salt and some water. What do I get at the end? Salt water. Are you going to have more salt and water at the end separate? Or are you going to have more salt water at the end separate? That's sort of what that means. So product favored means when you have a strong acid involved, it's generally going to have more product than it will reactants. It ionizes completely. In other words, these things are going to break apart and create separate things completely. They're not going to mix and match. They're just going to be separate. Okay? Weak acids. So what are some examples of weak acids? So weak acids are a little less excited about donating protons. I wrote proton giving. They don't like giving them away very much. They do, but they're not very happy about it. They're slow to do it. They may as well not at all. Um, they're reactant favored. So when you see a strong acid, or I'm sorry, when you see a weak acid, usually you have more on the left side of the equation than the right. Usually it makes less stuff than when you have a strong acid. It partially ionizes, which means it doesn't always break apart completely. Not always. Some examples of a weak acid would be, let's say, lithium hydroxide would be a weak acid. Potassium hydroxide would be a weak acid. Magnesium dihydroxide would be a weak acid. One more, you could really just put most of these in with an OH at the end. Calcium hydroxide is a weak acid. These are crappy acids. They're not really going to ionize very much. You'll usually have more reactants than products at the end, and they don't like giving away protons very much. All right. What about a weak base? Other than something that my first car had, it did not have good base. Weak bases are really crappy at accepting protons. Okay? Whereas a strong acid gives them up super easily, a weak base doesn't like taking them very much. And usually, since it doesn't really take that many, usually there are more reactants than there are products. There's more stuff left over from the reaction than there is stuff that was made. Some examples of weak bases would be, and you're about to see something interesting. Some weak bases would be, oh, I don't know, maybe some of these things. Hmm, do you notice something? What makes a strong acid is also what makes a weak base. Hmm, let's keep that in mind. What's next? What is a strong base? What does a strong base do? Other than something that my new car has, strong bases accept protons easily. They just grab them right up. They're also product favored. So normally you'll have more stuff made than you have left over from the beginning. You got more salt water at the end than you do salt and water separated. What are some examples of some strong bases? Oh, I don't know. Maybe some of these things, maybe some lithium hydroxide, some potassium hydroxide, some magnesium dihydroxide, and just for good measure, maybe some calcium hydroxide. Okay, the jig is up. Why are we repeating things? Well, what makes a strong base is also what makes a weak acid. What makes a weak base is what makes a strong acid. So, a way to think about this is if something makes a super good acid, it's probably not going to make a very good base. So it's a weak base. If something makes a super good base, it's probably not going to make that good of an acid. So it's going to be a weak acid. So, when it comes to accepting and donating protons, if you'll remember, that was largely, I believe, the Arrhenius model that talked a lot about protons and giving and taking those things. So, proton means hydrogen, right? An H. So an acid throws that H away, right? It creates hydrogen gas. So that H just leaves. With a base, it usually creates water, and it takes that H with it and makes something new. You'll also notice a pattern where the two weak ones favor reactants, while the two strong ones favor the products. How you can think about that is, when really strong things are reacting, it's making more stuff, right? If you put some hydrochloric acid in the middle of your car, it's probably going to melt some stuff and create some new stuff, right? If you put a if you spill some Coke, it's probably just going to puddle on the floor, right? That's a weak acid. It's not going to burn anything. You're going to have just Coke and car. You're not going to have melted metal. It's not creating anything. Okay, so some things to know. As if we're not covering enough things to know already, right? I lost my cover sheet. Some things to know about acids and bases. The equilibrium of reaction will go the direction of weaker acids and bases. I already kind of covered that. That's what I said, but in a different way. In other words, in the equation, where you find a weak acid or a weak base, you're probably going to see the direction of the equation pointing that way. And you'll see what I mean by pointing that way in just a second. The second thing, we talked about conjugate pairs of bases. In other words, what makes a strong acid is going to turn into a base, a weak base, and then what's a strong base will turn into a weak acid. So the conjugate pair of a strong base is a weak acid. I just said this. The conjugate pair of a strong base is a weak acid, and the conjugate pair of a weak base is a strong acid. So a strong acid makes a weak base, and a strong base makes a weak acid. That's what I just said, but in writing. I need to stop getting ahead of myself, y'all. I'm sorry. Pause it if you need to copy that. So let's talk about this. In a chemical equation, what do the arrows mean? You guys have seen this all the time, right? These little arrows, what the heck do they mean? If they are just stacked on top of each other like this, it's at a nice little equilibrium. That means it's not trying to make too much stuff, and it's not trying to hold too much stuff. It's just a happy reaction. Stuff's just working normally. If you see the arrow on the top pointing left really hard, the left is always the reactants and the right is always the products. That means that there's way more reactants left over than there are products. You got a lot of salt floating around and a lot of water floating around, and you didn't make very much salt water. So this means you are reactant favored. The third option is when that bottom one's big and it's pointing to the right really hard. What does that mean? That means you have way more product left over than you do reactants. You got a lot of salt water, and there's not a lot of salt floating around. So this is very product favored. That is what the arrows mean in chemical equations. And we're going to start seeing those in some examples. Now if I can find my examples, haha, I found my examples. So let's keep that handy. And let's look at some chemical equation examples. So, first example, and I get these from the book. If you look through these pages, I believe it's on around page 417. You can find these in the book too. This combines with that to create that and that. We know these names. Hydrochloric acid combines with water to create an ion of chlorine and a hydronium. Okay, that's fun enough. What's going on here? Is this at equilibrium? Is this product favored or is this reactant favored? Look at the arrows. It's all pointing to the right, which means you're not going to have a whole lot of this stuff left. It's going to be all that. That strong acid is going to combine with that water to create an ion with chlorine and a hydronium, which means this is product favored. I mean, the arrows kind of gave that away, but this is what's happening. Okay? So let's check this out. You have HC2H3O2. Ooh, that's a big one. When it's big and when there's C's, that's usually not a very strong acid. Those carbons really make it a weak acid. So this mess, added to the water, is going to create some C2H3O2 minus plus some hydronium. Okay, so this arrow is pointing to the left. Why is it reactant favored? Why the heck is it reactant favored? Well, if we look at our little list, weak stuff usually makes it favored there. And this has a lot of carbons in it. And carbon stuff is usually not very strong. Remember we talked about stuff that's on the far this side and far that side of the periodic table? That's what's usually strong. This has got some middle carbons, man. Middle carbons, they ain't strong. So when you throw this into the mix, it's going to go toward the weak stuff. The weak stuff can't make all that. It's not going to make all of it. That's the Coke in the car seat, man. So this is going to be reactant favored. Okay, looking back at number one. What is HCl? That is a strong acid. How do I know? Well, I just know because I gave it as the list, but if you look on page 419, there's this big old list here that tells you how strong different acids and bases are. That is a good list, and you're going to need it for your homework, so just good to know. So this strong acid kind of explains that. That's a weak acid. You didn't see anything here. I explained this very poorly. This is our weak acid. It's weak because it has all those C's in there, and if you look at the list, it's not in there. And it's an acid because it's donating an H, right? Acids give those H's away. And if this is giving away an H, that means that when it is moved over here, it becomes our conjugate base. Hope that makes sense. On what we've talked about, for homework, I want you to do number 4 on page 424. It's about identifying strong acids and weak bases and all that jazz. For my personal homework assignment, I only have one problem for you. I would like you to write your own equilibrium equation, okay? Just like these ones. I want you to write your own. Feel free to use Google if you struggle with it. Make sure to tell me where is it favored. All right, get the arrows right. List which one's the strong acid, the weak acid, strong base, and weak base. Whatever's important. And tell me what the conjugate acid or base is. Okay? I know what the book says and I know what I said. Please don't copy my problems, okay? Best of luck to you. This was a little bit of a scatterbrained lesson. I tried not to cover too much ground though. If you need any help, feel free to reach out on the text. But other than that, I hope you guys have a splendid rest of your Thursday. Where is my mouse? That is, if I can even find my mouse. If you, this might be kind of cool to show you. If you're wondering what my setup is like, bonus time. So I have my desk. Here's my laptop set up here. Oh, this does not look good. Hang on. My laptop set up here, and I have another monitor set up right here. That monitor is how I see what you see. That's why I'm always looking up all the time. And then this laptop is what's actually running my software. Cool stuff. I noticed, because I'm always looking up there, because that shows me what my monitor shows, so I can see if I'm teaching right. But then I look up there and I realize, shoot, I'm not looking at you guys, so I have to look back down here. That explains the weird tossing and turning. But anyway, yeah, bye. I still haven't found my mouse. I can't even turn it off. There we go.